All right, guys. So I actually had kind of an idea. So hopefully this idea is okay. But essentially, I decided to do an example with resistive forces before I do things like pulleys, springs, etc. And the reason why I'm doing that is because resistive forces is more of a physics-y topic, whereas things like pulleys, springs, etc. Those were all topics that were covered in Physics 1. So while I do still want to talk a little bit more about them and do an example with all of those things as well, I do feel like air resistance is going to be a little bit, or resistive forces rather, section 2.9 for College Board is actually going to be a lot more helpful of a video. Given that the 2025 AP exams are, coming up pretty soon. So that way, at the very least, if I can't get out some more videos, then hopefully this one you'll find to be a little bit more helpful, especially because it deals with differential equations, which is something that College Board loves to ask, whether that be for resistive forces, for oscillation questions, for RC circuits and E&M, or for RL circuits. College Board has a lot of different ways that they can talk about resistive forces or ask you questions about it. Sorry, differential equations. And they have a lot of ways that they can ask you about that. And I want to, hopefully use this video to help you feel a little bit more comfortable with it. How you we'll talk a little bit about that later, but essentially, right, this is the example that I want to work with is you have a box that's on a smooth ramp, so no friction. However, it does have a resistive force on it, and this box starts off by going up a ramp with some initial velocity, and this question is going to ask us for a couple of different things. We're going to have to draw the free body diagram for the object. We're going to have to derive but not solve a differential equation that could be used to describe the object's velocity as a function of time. We'll spend quite a bit of time talking about that one. We'll actually solve that differential equation and then sketch the acceleration as a function of time. So kind of a nice set of skills for us to feel comfortable with. So let's start with the free body diagram. Well, the forces that we should expect to be acting on this block, there's always gravitational force, so we do have to draw that. That will be pointed just straight down, just like usual, right? To the center of the Earth, but this is an object that's going to be close to the surface of the Earth at all times, so gravity is going to be down in that case. Velocity is not a force. We do not put that on our free body diagram. However, there are two other forces that this object will experience. A normal force perpendicular to the actual surface. So that should look something like this. And then you also expect there to be a resistive force that's going to be pointed directly opposite the direction of motion. So we'll label that FR. Now, in terms of the lengths of your vectors, what you should expect, and I'm going to redraw a couple of these, you should expect that you have your gravitational force again pointing down and your normal force pointing at an angle, just like we have on our actual diagram. How do you know how big to draw these forces? Well, we know that the box should not be going into the ramp and it should not be flying off of the ramp. So what I expect then is I expect that the normal force should cancel with this component of gravitational force that is actually pointed into the ramp then. So that way the net force of the block, if I were to have like say a tilted coordinate system and have y going out of the ramp and say x going up the ramp. Sorry, my drawing's a little bit bad here. So x is going up the ramp, y is going out of the ramp. I expect for all of the y forces to cancel out. I like to place in my free body diagrams the x direction as the direction of the acceleration. So here, the y component of gravity, which is into the ramp, will cancel with the normal force. Now, what about the x components? Well, we don't really know which one should be bigger, and the resistive force is, of course, going to change as the object slows down. So we can't really draw much in terms of like resistive force length versus the x component of gravity. Both of them are pointing the same direction. That's about all we can say, and that's, really about all we care about right now. So if you know the magnitudes of forces or you know things are supposed to be canceling out, draw them as such. And if you have absolutely no way of comparing them, then it's fine to just get their directions like we did with resistive force here. So, good. All right, next part, derive but do not solve a differential equation that could be used to describe the block's velocity as a function of time. Well, how do we approach this? Well, anytime you see the words differential equation, velocity, and time, you always have to start with one law in particular. That law is Newton's second law. Now, whenever you're talking about just the words differential equation in mechanics, always Newton's second law. But for electricity and magnetism, there's another law that they might ask you to use. However, anytime you're working with just mechanics quantities in a differential equation, so velocity, position, time, they're always going to start with Newton's second law. Anytime you're working with electrical quantities, your differential equation, you should start off by writing down Kirchhoff's loop rule. That's a long way away, but hopefully you've learned about it by now if you're taking the AP exam and you're watching this video to study for your AP exam. But if it's early in the year, don't worry about that. Your teacher should teach you about Kirchhoff's loop rule when you get there. So again, for mechanics, differential equation, whenever you're using it to find velocity, position, or acceleration, you're going to have to start with Newton's second law. Why do we do that? Well, acceleration is the derivative of velocity. So that's why. So we can say then that mass times the derivative of velocity with respect to time, that's our ma, is equal to net force. Well, what's our net force in this case? We have both a resistive force and part of gravity pointing down the ramp. So both of those are going to be important. We do know that the component of gravity down the ramp is mg sine theta, and then our resistive force is just b times the velocity. How do I know that the component of gravity down the ramp is sine? Well, imagine that you make the ramp steeper. Your angle is going to get closer to 90 degrees, and you expect for this component of gravity, the part that's actually responsible for accelerating your object, to get bigger. Conversely, if your surface gets flatter, the angle goes to zero. Your angle of inclination for your ramp goes to zero, and you expect for the block to not have any acceleration. Sine follows those trends, cosine does not. There is a way to geometrically derive whether it's sine or cosine. I don't think it's worth the time on the AP exam. I think it's worth knowing that the component of gravity down a ramp is given by the sine of the angle and not the cosine. So, it's fine if you're trying to learn it for the first time to try to derive it, but if you're using this for review, I think it's more helpful to think about it conceptually first. So, yeah. And then if we wanted to turn this into a differential equation, well, it's actually already done for us. This is a differential equation. It has a derivative of the function you're trying to get, as well as the actual function itself. So it has dv dt and it has v. Both of those are functions of time, and we should be able to then solve that potentially to find velocity as a function of time. How do we do that? Which is the next part of our question. We're going to have to exploit a process called separation of variables. How that works is you have to get everything that depends on velocity on one side of your equation and everything that depends on time on the other side. So in this case, we'll end up, if we rearrange that equation up above, with a negative dv over mg sine theta plus bv. So I pulled out that negative sign is equal to 1 over m dt then. And now I actually want to do an integral on both sides in order to solve for velocity as a function of time. Now, why does separation of variables actually work? Well, typically what separation of variables looks like is you have a derivative. In our case, it's dv dt, but it could also just be f as a function of time. F is not a force, it's just a general function. And you would be able to say then that you could split up the rest of your differential equation. So say this mg sine phi minus bv into some function that depends only on f and some function that depends only on time. And so therefore, if you rearrange it, you're going to end up with integral of 1 over g f df. Whoops, sorry. That's not what I meant to do. If you rearrange it, what you're going to end up with is df dt times 1 over g of f. Sorry, I'm going to rewrite that. I did not leave enough room there. So 1 over g of f df dt is equal to h of t. Now, again, if you're kind of confused about what I'm doing, I'm kind of just showing you what the process behind separation of variables looks like. You don't have to know this for AP exam or anything. You have to know how to use separation of variables, but this is why it works. If you can separate your right side of your equation in our case, so the side that's not the derivative, into something that depends on your dependent variable, which in our general form is just f, but in our specific case is v, velocity, and your independent variable, t, or time, then you can rearrange that differential equation to look something like what I have just written down. Now, if you integrate both sides with respect to time, you have to do integral with respect to time. Look at that. The dt's cancel out, and you're left with integral of df over g of f equals integral of h of t with respect to time. Now, going back to our situation, okay, well, what's g of f and what's h of t then? Well, g of f is going to be equal to negative mg sine theta minus bv, and h of t is actually just going to be 1. So if we follow that same process, well, look at that. The v equation, g of v, has nothing with time in it. Yes, velocity depends on time, but we're treating them as two separate variables here, an independent and a dependent variable. Right? So the g of v equation doesn't depend on time, and the h of t equation does not depend on velocity. So that is something we can separate, and therefore we can apply separation of variables. Based on our equation sheet, if we actually solve what we have written down for our two integrals, then, well, on the right side, you're going to have a very simple integral. You'll get t over mass plus an integration constant. On the right side, it's a little bit more difficult, but it does end up giving you a natural log. So you're going to end up with, oh boy, it's been a while since I've done this, but I'm actually going to work it out using u substitution just to make sure I don't make a mistake. So u is going to be that du times 1 over b will give you dv then. Okay, yeah. So that works pretty well. You're going to get a negative 1 over b times natural log of mg sine theta plus bv then. And if you simplify or rearrange, because we wanted to solve for velocity, well, what you're going to get is mg sine theta plus bv equals a constant times e to the negative bt over m. So if you wanted to solve that for velocity, pretty easy to do that now, right? Move the mg sine theta over to the other side, divide everything by v, so you get v of t equals a constant e to the negative b over m times t minus mg over b sine of theta. Now, notice that I've just kind of kept my integration constant as c, and that's because it really doesn't matter. It's some unknown constant that we're now going to solve for. How do we solve for that? Well, we already know that the velocity at time 0 is given to be v of 0. So that means that v0 is equal to c minus mg over b sine theta. So then c will be v0 plus mg over b sine theta. That then tells us that the velocity as a function of time is going to be given by, let's see, mg over b sine theta e to the bt over m minus 1 plus v0 e to the negative bt over m. Wow, okay. Not a very nice equation, but it works. Now you're probably looking at this and if you're somebody who likes to evaluate expressions, what you're going to notice is that as t goes to infinity, this value does not approach a nice thing. It approaches as t goes to infinity. We'll talk about the acceleration in just a minute, so I'm going to section this part off here. But if you were to, again, plug in t goes to infinity, you're going to find that the velocity approaches a negative mg over b sine phi. Well, is that really expected? Not really. You don't expect the block to actually really end up going down the ramp if you let it go up the ramp for an infinite amount of time. But at the same time, you also don't expect the block to go up for an infinite amount of time either. The block is eventually going to stop. And when it stops, gravity will cause it to come back down, and the resistive force will actually change direction. So this equation for velocity is actually only valid until the block stops. Right? It's not valid until the time of infinity. So this like plugging in bounds part, well, that doesn't really make much sense. On the other hand, if you plug in t is equal to 0, right? Well, now what you're going to end up getting is just a value for v of 0 is equal to v0 as we expect it to. So that one does make sense. So it's helpful to evaluate the bounds, but you also want to think physically about this, right? It's helpful to evaluate the limits, but think physically. Do you expect the block to be going up for infinite amount of time? And if not, is this equation still going to be valid? It's not, which is why in the problem I specified up until it stops, or until it stops, find the block's velocity as a function of time. All right. How do you sketch the acceleration as a function of time? And we'll say until it stops again. I forgot to write that as usual. But what you have to do is you have to first find the acceleration. Well, that's equal to the derivative of velocity, which is going to give you a negative g sine theta e to the negative bt over m minus bv0 over m e to the negative bt over m. So you're actually getting an exponential decay, but it starts at a negative as it should because our positive was up the ramp. So this thing will have a negative acceleration, aka net force down the ramp. So it starts off at a value of negative g sine theta minus bv0 over m, and it'll approach 0 then. So it should look something along the lines of that then. All right. Okay. So before we end off, then just a couple notes about this problem. Number one, probably a little bit more complicated than you would actually have to do. This is a case with air resistance that has a bunch of different forces acting on it. My assumption or guess or hope, we'll call it my hope. My hope is that College Board will not make you do air resistance on a ramp. So, hopefully you're able to kind of follow these steps. And if not, I encourage you to maybe try to work it out as well, because if you can solve an example like this, then that should be a good sign for whatever College Board throws at you. Notice that you have a free body diagram, a couple of derivations, and then a sketch of something as well. So while it doesn't 100% follow the free response question formats that they might throw at you, it does cover a lot of skills that they might, like sketching graphs, doing some mathematical derivations, starting with a physical law, and drawing free body diagrams as well. So good things to keep in mind. Other things they might ask you in questions like this is to change the scenario a little bit and then ask whether your equation or graph supports a conclusion that they're giving you. So best thing to do with that is to kind of look at the College Board resources. We don't yet have too many good free response questions to kind of go off of. So, trying to mainly show you what sort of skills you might have to use. Not necessarily as a full free response question, but just overall. So, thank you guys for watching. Yeah, that'll do it for this video. And in the next one, we'll take a look at some, a little bit more tame forces problems, things like springs, pulleys. Yeah, have a great rest of your day.